Okay, good morning, everyone. I hope you're all doing well. So there was a lab due last night at midnight. I think I saw that there were 14 submissions out of the 18. So a couple people who weren't able to submit, if that was you, and it was more like a logistical thing, like you did it, but you can't figure out how to get it in, stay after class. And we can do a share screen and I can walk you through how to submit that. If you have any questions on that, let me know as soon as possible. I can give you, if you had it done last night and you're just trying to get it in the computer, I can give y'all a grace period, for a day for this first round. So just let me know. Hopefully you're able to get the Mastering Chemistry in as well. And we're going to move forward to chapter 3. So chapter 2 was a lot of math, and there are going to be certain chapters that are more math based. But we're going to take a break from math for a little bit here until the end of this chapter and do a lot more concept based stuff. So chapter 3 is all on matter and energy. So this is sort of like if we think of the universe in its entirety, everything in the universe. The universe is at the top of this chart. We can break it down into either being classified as matter or being classified as energy. And then we can, cut those up farther down. So we can break matter up and we can break energy up into different types. So as far as atoms and molecules are concerned, these are sort of the basic building blocks of matter. Everything that you can see around you is composed of matter. And then there are a lot of things in the room around you that you can't see that are also composed of matter. So microscopic dust particles, air is made up of matter. It's just very, very low density. We don't see it. The coffee you're drinking, whatever the table you're sitting at, it's everywhere. Chemistry is everywhere. Woohoo. Okay, moving on from that. So what do we define matter as? So in order for it to be classified as matter, it has to occupy space, and that could be a very small amount of space, okay? It's very, very teeny tiny, but it has to occupy space, and it has to have some amount of mass to it. So some types of matter like steel, water, wood, plastic, these are all easy to see with the eye. Then there's microscopic dust and air, which you would need some sort of magnification. Our eyes aren't strong enough to pick that up. From a human scale, because we kind of always think of things as like on the human level, right? Because we're human beings. So on the human scale, when we look around, matter feels relatively continuous, right? When you rub your hand over the desk, when you take your finger over the screen of your iPhone, it feels like it's a continuous solid surface. But that is not actually the case for matter. Matter, when we break it down into its most basic particles, is not continuous. So there will be areas where we have more matter and areas where we have less matter. Ultimately, the most basic building block of matter that is identifiable or unique would be an atom. The difference between an atom and a molecule: an atom is a single element. A molecule is going to be when you have multiple atoms bonded together. Okay, so you can, if we're thinking about like, for instance, the English language, atoms would be the letters, molecules would be like short words. Okay. A molecule will have a very specific formula. So in order for it to be, let's say, a water molecule, it has to have 2 hydrogens bonded to 1 oxygen. It has a signature formula to it. So here's an aluminum can. This would be an example of a state of matter that is composed of just atoms. So we just have these little aluminum atoms lined up with each other. From the macroscopic level, or from the human level, the can looks smooth and continuous. But when we go down to its atomic level, what we'll see is that there are actually these balls of atoms where we have matter, and then there's space in between them, right? And if we go ahead and break these atoms down even farther into their subatomic particles, which we will a little bit later, it's mostly empty space. And then concentrations of matter. So it isn't this smooth situation. Here's a container of isopropyl alcohol, which is just rubbing alcohol. This is composed of molecules. So here is an isopropyl alcohol molecule. I wouldn't expect you to have that molecule memorized or anything like that. But what you're seeing is that there's a clumping together of atoms in a very specific formula. So every one of these things has one of these red guys on it, right? That's sort of at the end. And there's a series of black and white atoms, which are carbons and hydrogens. These molecules act as packets. For the most part, they're not going to break apart unless you run it through like a chemical reaction. So we don't need to talk about this or scanning. Let's move on from there. Okay, so the common states of matter. So there are 3 common states to matter. It exists as solid, liquid, or gas. We like to classify the matter that we're describing by its state as well. So if I'm saying, hey, I have H2O, I would want to add a little L to the end of it to say it's liquid, it's water, or I'd want to add an S to it to say that it's ice. There is another state of matter outside of this known as plasma, which happens at very, very, very high temperature, low pressure environments. It's when the electrons like don't even stay with their own atoms. A lot of the universe is made of plasma, but we won't be working with that. So we're going to stick with solids, liquids, and gases. Water is a really unique compound in that it exists as a solid, a liquid, and a gas in a very narrow window, temperature window, and we happen to live in that temperature window, right? So we see all 3 of those states around us. Depending on where you are on a hill or mountain today, you may be seeing ice, I'm seeing water, and you may be seeing steam, right? If there's some evaporation happening. So how do these different states relate to each other? So here is, all of these are made out of these little H2O molecules. When we're dealing with a solid, okay, which is ice, the water molecules are going to be closely spaced together. So solids tend to be compact. And there is a small amount of vibration between the adjacent molecules. You're always going to have a little bit of vibration because they have energy to them. But they're going to stay in a fixed, rigid shape. So you can kind of think of your solid form of material as there's soldiers in an army, and they're all lined up, and they're all facing the same direction, very rigid. Well, what happens if we start to heat our solid up? So we add some thermal energy to it. That thermal energy is going to convert into kinetic energy or movement. So we're going to start to get vibration. And this vibration will overpower the crystalline structure or the alignment in solid form. And these things will start to be able to roll past each other. Okay, so we can think that maybe these soldiers started, I don't know, like drinking a little bit of alcohol, right? And they've got a little bit of energy to them now. And so now they're kind of dancing or rolling past each other. They're still closely packed together though. Okay, so when we move into a liquid form, we lose the alignment, but we keep everything really close together. In a gas, so if we're moving from a liquid to a gas again, how do we do that? We can add thermal energy. You can also depressurize it, but for right now, we'll just talk about temperature changes. As we add heat, these soldiers now want to get as far away from each other as they can. So it's not just that they've lost their arrangement here. They've also, when they move to a gaseous form, they lose that compacted quality to them. So we'll see here, ice again, or a solid is going to be close together with a fixed point. Liquids are going to be closely spaced, but they're free to move past each other. And then steam or a gas, they are separated by large distances. They also have a very small amount of interaction. So these things kind of stick to each other, right? Obviously, these are stuck to each other because we have a solid. Liquid, there is something known as surface tension, right? Water will kind of stick to itself. Steam won't do that because there's so much distance between them. So kind of going over all of this, but we already talked about this, but in solid, right, they're packed closely together. They have a fixed location. Neighboring atoms or molecules in solids will have some vibration, but there's not enough vibration for them to move past each other. This is important here. Solids have a fixed volume and a rigid shape. So if I take like a spoon, for instance, and I stick it in a cup, it's still going to have the same shape and it's still going to have the same volume. The spoon itself doesn't change because it's solid. Ice, diamond, quartz, iron, whatever, lots of examples of solid material. On your periodic chart, most of the metals are going to be solid. There is one out there that isn't, mercury, but most of them are solid. We can classify solids as either being a crystalline solid or an amorphous solid. So a crystalline solid is something that's going to have this sort of long range order, where we have this repeating order, like salt does this. An amorphous solid is one that has short range order. So the soldiers right next to each other are aligned, but they sort of get lazy and the soldiers start to kind of like move in a different direction as you move away. This would be something like glass and rubber or plastic. There's a picture here. This would be our crystalline solid, very, very structured across the entire sample. Here we may have a little bit of alignment, right, on a smaller scale, but over a bigger scale, no long range order. So there's sodium chloride, which is just a nomenclatured way of saying table salt. We can see long range order. A lot of times when you have this long range order with the atoms, you'll actually see it on a macroscopic scale as well, or a human cell. It'll grow in these nice crystalline shapes. So liquids, because they have a little bit more kinetic energy to them, the molecules are close together, but they can roll past each other. So since they're close together, they still have a fixed volume, but they can change shape. So if I have 100 milliliters of water in a coffee cup, and I pour that 100 milliliters of water into a graduated cylinder, the shape of it will change, right? The water fills up the shape of the container, but the volume won't change. It'll still read 100 milliliters. Water, gasoline, alcohol, and mercury are all examples of liquids. The last one, gas, which gases are really interesting, and we will actually later on in the semester spend an entire chapter just talking about gases. They are the highest thermal energy or kinetic energy of the 3 states of matter. So because they have so much kinetic energy, these molecules or atoms are moving really quickly past each other. They're going to take up a big distance. They're going to try and create a lot of space, and they don't really interact with each other. So you can kind of think of the atoms like billiard balls. They're just moving through space independently, and they may like hit into each other, but if they hit into each other, they'll just ricochet off. So we don't get any sort of like clumping of the atoms or molecules in a gas. They just sort of spread out. Now, because they don't interact with each other or clump together, that means that gases will, not only will they change shape, but they will also change volume. So they'll fill up the entire container that they're in. So if you have like a container of compressed gas and you release that gas into the room that you're sitting in, the gas that you have will spread out to fill the entire room. And then let's say you open your door, that gas will then spread out of your house into the surrounding area and will spread out and dissipate as much as it can. So gas will always assume the shape and the volume of whatever container it's in. Now, because of this, that means that gases are compressible. The other 2 states of matter are not, gases are. So you can take, the amount of gas that's in, let's say this room here, and you can shrink it down into a small compressed container. Oxygen, helium, carbon dioxide, all examples of gases. So solids are not compressible. Gases, because they have so much space and they're not interacting, those are compressible. Liquids are not compressible as well, okay? You cannot compress a container of water. That would require a lot of force. So this is a good chart that sort of just has all that information compiled. Hopefully some of this feels relatively intuitive, but you do want to know the different states of matter and how they affect shape, volume, and compressibility. So let's talk about matter. And you can draw yourself a little diagram. And at the very top, or a little flow chart here, at the very top, we're going to put matter. So in order for it to be classified as matter, what does it need? It needs to take up space and it needs to have mass. Now from there, we can actually break it up into two different things. We can say that it's either a pure substance, or we can say it's a mixture. And how do we differentiate pure substances from mixture? Excuse me. A pure substance is going to be composed of only one type of atom or molecule. And remember, a molecule is something that has a fixed elemental ratio. So like water, for instance, H2O. Those are bonded together. They have a fixed formula. A mixture is going to be composed of two or more different types of atoms or molecules. The key thing with a mixture is that you can change the proportions of whatever the things are that you're mixing. So water, whether I have a drop of water or a cup of water, it's always going to be a ratio of 2 hydrogens to 1 oxygen. If I have something like salt water, that would be a mixture. Why? Because I can add more salt or I can take salt away, or I can add more water. I can shift the proportionality of salt to water. So with a pure substance, I can break it down into an element or a compound. So let's fill that in over here. Element or compound. So in order to be an element, you have to be something that can't be broken down into a simpler, I want to say simpler identifiable substance. Okay, so water isn't an element. I can break water down into hydrogen and oxygen. Hydrogen is an example of an element. If I break hydrogen down into its simpler particles, it becomes protons, neutrons, and electrons. Protons from hydrogen and protons from oxygen are the same protons. So there's nothing unique about it, right? So it's the simplest unique piece of matter. No chemical transformation can decompose an element into a simpler substance. So I can't take, oxygen and go through a chemical process that would break it down into something simpler. All known elements are listed on a periodic table. Here's my periodic table that I've been using for a while now. You will want to have access to a periodic table. The textbook has a periodic table. The lab manual does as well. I like to have a paper one because then you can like write all over it, which you're going to want to do. Give yourself some notes. So all of those things on there are elements. Each box is its own unique element. A periodic table, can be found in your chart. Okay, so we will spend more time on the elements in the next chapter. An example of an element is helium. Right, here's a balloon. It's filled with just helium atoms. Let's say that there was no air from the surrounding room that seeped into here. It's just filled with helium. A compound is a type of pure substance, but it's two or more elements that are fused together in fixed and definite proportions. So they've bonded together. Most elements don't like to be by themselves, all right? Usually the things around you are not in elemental form. They are in a compound form. They're elements that have bonded to something else because they're reactive. So they're more stable when they partner up. Kind of like people, right? Sometimes we tend to be more stable when we have a community around us, so they bond. Water, table salt, sugar, they're all examples of compounds. How many elements are there? I mean, give or take about 110. How many compounds are there? Thousands and thousands and thousands, okay? How many of the compounds do you have to have memorized? Not really, you don't have to memorize them, all right? And know that water is H2O. That's probably gonna get you through this class. You will need to know how to name them, which we'll talk about in a couple chapters, but I don't expect you to know what sugar is. Okay? I do expect you to know what table salt is. Table salt is NaCl. But I don't expect you to know the compound of sugar, things like that. Compounds can be decomposed into something simpler, right? So I could take water, H2O, hook it up to a really simple contraption with a battery, and I can separate it into hydrogen and oxygen. So here is a pure substance. This is water. This looks like it's coming from a water fountain or something, so it's actually probably not a pure substance. There's probably some other things floating around in there, but let's just say it's distilled water, so it's just H2O. Doesn't matter if you have a little bit of this or you have an entire room or swimming pool full of this, it's always going to be fixed proportion, 2 hydrogens to 1 oxygen. You can write a compound with a chemical formula. So let's give a couple examples here. So an element, right, we're going to say examples of this, helium or hydrogen, helium, iron, anything you find on the periodic chart. Compound, H2O, NaCl, H3O plus, anything that has this sort of distinct chemical compound or chemical formula. All right. So I think where people tend to get a little bit confused is compounds and mixtures, because they're like, well, it's 2 things, it's 2 or more things, right? Well, a compound is going to be a pure substance composed of 2 atoms, 2 different atoms that are chemically bonded together in fixed proportions. A mixture, on the other hand, is going to be 2 different things that are not bonded to each other. They're just in the same container, mixed together. So some examples of mixtures here at this pretty beach. The water is an example of a mixture. This is along the ocean. So we have water and salt. And the salt is actually broken up into its ions, which we will get more comfortable with later on in the semester. But what we have is 2 different things that are mixed together. Could there be more salt in here? Yeah, you could put more salt in, or we could add more water. The air is also an example of a mixture. It's got nitrogen and oxygen, and there's some argon in there and some CO2. So again, the oxygen and the nitrogen, these aren't bonded to each other. They just happen to be in the same container, which is the sky. So a pure substance may be either an element, such as copper, or a compound, such as sugar. A mixture, now we're going to break into either being a homogeneous or a homogeneous mixture, or a heterogeneous mixture, okay? So let's add to our little chart over here. We're going to break our mixtures down into heterogeneous or homogeneous. Okay. How we differentiate those 2 things from each other. A homogeneous mixture is a mixture that's the same throughout. So it's evenly mixed, such as sweetened tea. All right, think about the root here for homogeneous, homo, the same. Heterogeneous, hetero, different. So a heterogeneous mixture is going to have inconsistencies in its proportionality. So hydrocarbon and water, or oil and vinegar. If I have oil and vinegar, even if I shake it up, there's still going to be like globulars of oil, right? So depending on where I take a sample, it could be more oil, it could be more vinegar. So homogeneous, evenly mixed; heterogeneous, not evenly mixed. So this is sort of the chart that we've already drawn here. but we've got our matter. We can break it up into a bunch of different things. Homogeneous, there's our sugar and our tea. Heterogeneous, here we've got the water, and then the oil is sitting on top. They're not mixing together. So let's see an example. The other, I'll give you a couple things, and I want you to tell me. Here we go. Tell me what you would classify them as. So an example. Let's see. So I've got CCl4, aluminum, bananas and oatmeal, and sulfuric acid. Okay, so let me know, are those heterogeneous, homogeneous, an element, or a compound? You don't actually have to tell me, just I'll give you a minute to conceptualize. Okay, so for this first one, CCl4, you may be like, I don't know what this is. Who knows what this is? What does it do? Well, it is a chemical formula. Okay, this is carbon tetrachloride. But you don't even really need to know that. You just need to know that it's written as a chemical formula. If it can be written as a chemical formula, it's a compound. Okay. Aluminum. Aluminum is just Al. It's just what it says, aluminum. So this is going to be an element. Bananas and oatmeal. That is a mixture, specifically a heterogeneous. And if you don't believe me on that, how many times have you eaten banana and oatmeal and you like pick out the things you like, right? Like your first couple bites have like a lot of banana in them and they're like super good. And then towards the end, you're just left with the oatmeal. So every bite is a little inconsistent. Sulfuric acid, this is a compound. You can write this as a chemical formula. Okay, you may not know the chemical formula for sulfuric acid, but it can be written as a chemical formula. That one was a little tricky. Any questions on classifying matter? You should have some things in your homework where it tells you to do just that, right? Put it in one of those categories. All right, so this is just a summary. We can move on from there. Excuse me, hold on. Okay, so different kinds of matter will have different types of properties. So if I'm looking at a piece of matter that is made of aluminum versus a piece of matter that's made of sulfuric acid, the aluminum matter is going to have physical properties and chemical properties that are unique to it. Sulfuric acid will also have physical and chemical properties that are unique to that substance. So when classifying a physical property is anything that a material displays without having to change its composition. So gold is shiny. That would be a physical property. The gold doesn't have to like become something new to show you that it's shiny. A chemical property is one that a substance can display only when it goes through some sort of change in composition. So an example of a chemical property would be gasoline's flammability. In order for gasoline to show you that it's flammable, right, or to see this flammability property, it has to combust and become something new. Specifically, it becomes carbon dioxide and H2O. So examples of physical properties: color, odor, appearance. Examples of chemical properties: combustion, oxidation, reduction, things that involve some sort of change. So when talking about gasoline, right, the odor of gasoline is a physical property. Gasoline doesn't have to change in order for you to smell it. The gasoline is, what is happening is the gasoline is changing state. So it's going from a liquid in your gas can, and it's volatilizing, or it's turning into a gas. And the gas molecules of the gasoline are hitting receptors in your nose. It's not actually the gas that's doing it. There's a substance in there that they make it smell. Gasoline itself doesn't have an odor, but they put something in there so that you can smell it. The flammability of gasoline would be a chemical property. So with this, this idea of changing states, going from a liquid to a gas, all physical changes, so going from a solid to a liquid or a liquid to a gas, or sorry, phase changes, are physical properties. So the boiling point of water is not a chemical property, it's a physical property. What happens when we boil water? We're just changing its state, but we're not changing what it actually is, right? It's going from liquid H2O to gaseous H2O. It's still H2O. So the atomic or molecular composition of a substance does not change when it displays physical properties. So the boiling point of water would be classified as a physical property. It may look like it's doing something kind of chemically, oh, it's disappearing or it's bubbling. It's just going into a new phase. So here we go. We've got liquid water and their H2O molecules. We've got gaseous, water vapor, they're still H2O molecules. They're just farther away from each other. Nothing has changed in their chemical composition. No, Sarah asks, so would combustion also be a physical property? No, combustion would be a chemical property because in order to combust something, and I will write an equation, if I'm going to combust methane, you have methane, it has to combine with oxygen to produce CO2 and H2O. We started with methane, we ended up with new materials. These are not the same as this. So if I can write it as a chemical equation, it's a chemical property. Some indicators that a chemical change has occurred: if you see if heat is produced, or if the thing gets really cold. And I'm not talking you put it in the freezer and it gets cold. I'm saying two things mixed together and all of a sudden it gets cold, or two things mixed together and all of a sudden it gets super hot. If you produce light, if these are, yeah, great, Sarah. Okay. These are all indicators that some sort of chemical change has occurred. So again, these slides start to get kind of redundant, but in a physical change, matter changes its appearance, but not its composition. When ice melts, it looks different, but it's still made of H2O. In a chemical change, matter does change its composition. So if you have a piece of copper, or you have copper pots and they start to turn green, they start to patina, what is happening is that copper is reacting with oxygen in the air, and it's actually forming a new compound. It's forming a copper oxide. This new material is indicating that there's a chemical change. Here is another example. So we've got a nail here. When it's a fresh nail, it's just made of iron. If that nail has sat out for a while, it will actually begin to pull oxygen out of the air and form this thing called iron 3 oxide, which is rust. Rust is an indicator that there's a chemical change. If there is a chemical change, we should be able to write what's known as a chemical reaction. And we are going to spend a whole chapter talking about chemical reactions. So for right now, we just want the basics. This is the setup for a chemical reaction. You read it like you would read a book. So you read from left to right. Reactants go on the left side. There will be an arrow. And then on the right side, you will have your products. The arrow is indicating that the chemical change has occurred. How many reactants can you have? You have to have one, a minimum of one, and you could have, hundreds. For this class, we'll probably max out at 2 or 3. Products, again, you have to have a minimum of one. If you don't have any products, then you haven't undergone a chemical change. So you have to have at least one. Again, you could have a lot more than one, but we'll probably stick with, 2 to 3 on both sides. So again, just to hit it home, a physical change results in a different form of the same material. A chemical change results in totally new materials. If we've got a lighter over here, a butane lighter, if you've ever played around with a butane lighter and you don't strike it, you just hit the little plunger. All you're doing is releasing the butane or allowing it to volatilize. So the liquid butane is becoming a gaseous form of butane, but it's still butane. Now, if I actually strike the flint with it as well, I'm going to combust it. That butane is going to turn into CO2 and H2O. This would be a chemical change, right? These are different than what we started with. Here, these are the same. It's just a different phase. So this process of distillation is where we can separate mixtures through physical changes. So I'm not running any sort of chemical change. So let's say I have water here and it's got salt in it. If I want to separate out the water and the salt, it's a mixture, I can heat it up. The water will evaporate and then it can move through what's known as a condenser. So there's some cold water that's condensing it, and then you'll collect it over here. And then over here, we've got a receiving flask where we have separated out the salt from the water. We can also separate through a physical change, solids and liquids. If we've got a mixture, let's say we've got like a muddy water and we just want to collect the water, we can use some sort of filter paper, collect the liquid or the water and leave the solid particulates behind. So to go along with a chemical reaction, we want to talk about the law of conservation of mass. So this only applies to chemical reactions. It doesn't apply to nuclear reactions. We don't do nuclear chemistry in this class. You will do nuclear chemistry if you move into 151 or 130 after this. So this rule will work for you for the whole semester. And it says that in a chemical reaction, matter is neither created nor destroyed. So the amount of matter or material that you start with should always equal the amount of matter that you end with. It doesn't matter if those atoms have rearranged, have gotten new partners. You shouldn't have things just disappear. If you start with 3 aluminum atoms, you should end with 3 aluminum atoms. You can't end up having 2 aluminum atoms because where did that aluminum atom go? Did it just disappear into the ether? No, it is somewhere. So we need to take an account to it. So an example of this on a really, really basic level is suppose that we have 58 grams of butane in a lighter. It will react with 208 grams of oxygen to form 176 grams of carbon dioxide and 90 grams of water. I expect you to be able to write a chemical reaction from something like that, okay? I don't expect you to know the formula for butane or the formula for oxygen right now, but you should be able to write at least the name butane. And we can see here, suppose that butane reacts with oxygen. So we know those are 2 reactants. And it says to form. Anytime you see the word to form, to produce, that's the change. CO2, carbon dioxide, and water. We know how much of each we have. So we have 58 grams of butane and 208 grams of the oxygen. And it says we produce 176 grams of carbon dioxide and 90 grams of water. Those 2 values, when we add these together and these together, it's 266 on both sides. It should always equal in a chemical reaction. So I could give you 3 of the 4 of these. I could have given you the amount of butane, the amount of oxygen, and the amount of carbon dioxide and said how much water is produced. and you could just do an easy subtraction to figure out the missing component, because this side's total needs to equal this side's total, just based off the law of conservation of mass. Now, again, in a nuclear reaction, so what's happening in a nuclear bomb or in a nuclear reactor for power, that is a different situation. And in that, we will actually change matter into energy. So you can lose large quantities of matter pretty quickly. Okay, so we're going to leave matter behind. Let me see what time it is. Okay. We're going to leave matter behind, and we're going to talk about energy. So when we go back to, there's the universe, and we separate the universe into matter, and we classify matter as either a pure substance or a mixture. Now we're going to go in the other direction, and we're going to talk about energy. And energy is a little bit more elusive because you can't see it directly. You can only see like the effects of it, or like in a secondary way. But energy is so important, this concept of energy, because energy is what makes the universe interesting. If we didn't have energy, nothing would move, nothing would change, nothing. It would just be like matter doing nothing. So energy is definitely needed to make the universe unique and dynamic. As far as what we classify energy as, energy is the capacity to do work. And when I say work, I mean force over a given distance. But if you think, oh man, that's so much work, like lifting all that wood is work. It is work. In the physics sense and in the science sense, there's a specific definition for it that says the amount of force over a given distance. The more work you can do, the more energy is required, and vice versa. So all of the behavior of matter is driven by energy. We need to know energy in order to understand chemistry. So just like the law of conservation of mass, there is another thing called the law of conservation of energy. Energy in the universe is conserved. So we can't create energy and we can't destroy energy. That's why these perpetual motion machines are not a real deal thing, because you can't just pull energy out of nowhere. You have to have a source for your energy. So in order for you to go run a marathon, you need to consume calories. You need energy for that. The total amount of energy out there is constant. Energy can change from one form to another, and it can be transferred from one object or one chunk of matter into another chunk of matter, but it can't just come out of nowhere, and it can't just disappear into nowhere. So a couple different types of energy that we want to be familiar with. The total energy of a sample of matter is the sum of what we call its kinetic energy and its potential energy. So if I've got a hunk of matter, let's say we've got a hunk of CO2, it's going to have a certain amount of kinetic energy and it'll have a certain amount of potential energy to it. Kinetic energy is the energy associated with motion. Kinesiology, someone who goes into kinesiology is studying the motion of the body, so kinetics, movement. Potential energy is the energy that is, you can kind of think of that as stored energy in matter. That's associated with either its position or its composition. So a weight that's sitting on top of a house has a certain amount of potential energy because you've pulled it up against the force of gravity. So it's got this stored energy to it. It kind of wants to roll down the house and hit something. Composition, we can talk about that, actually jump down here to chemical energy. So chemical energy is a form of potential energy that's associated with the arrangement or the position of particles in a given system. So TNT, for instance, has a lot of chemical energy or potential energy. The way that those atoms are arranged makes it very unstable. It wants to explode. We've got another thing called electrical energy. This is the energy associated with the flow of an electrical charge. So, when you plug your iPhone in and you charge it up, that's what we're dealing with. Another one that's useful is this thermal energy. This is the energy associated with the random motions of atoms and molecules in matter. So all pieces of matter have some amount of thermal energy to them. If you add more heat, your thermal energy will increase. So what are the units for energy? We've got the joule. The SI unit is the joule. We see that one quite a bit. Named after James Joule. So it's going to be this capital J. We also have another unit called a calorie. And there is two different types of calories. Okay, we've got a little c calorie, which is written with a lowercase c. And then we have a big C or a capital C calorie. When you think about a nutritional calorie, that's the big C calorie. Okay, so when you're looking at a candy bar, those are big C calories. How does a big C calorie and a little c calorie relate to each other? Well, sometimes this big C calorie is also called a kilocalorie. It's 1,000 of those little C calories. Okay, so one of these big guys is equal to 1,000 of the little guys. We have another thing called the kilowatt hour, which is 1 kilojoule per second times 360 seconds in an hour. We don't spend a whole lot of time talking about the kilowatt hour in this class, but that is what's on your electrical bills. So let's look at some of those conversions. We've got 1 calorie, 1 little c calorie is equal to 4.184 joules. And this number will pop up again. 1 big C calorie is equal to 1,000 little C calories. And then 1 kilowatt hour is equal to 3.60 times 10 to the 6 joules. Again, I don't do a whole lot with this last one, but these two I do want you to know. So what do we got there? 225. Okay. So using these two conversions factors, because these are conversion factors, right? This equals this. This equals this. I want you to tell me, say that you're given that you have a little candy bar. Okay, well, it's not really that little. Let's say it's got 650 big C calories. Okay. So I want you to find how many joules this is of energy. How many joules of energy are stored in 650 big C calories? So I'll give you all 2 minutes to go through that. So let's say, yeah, the 650 calories, that's like a bigger candy bar. That's the big guy. Not the hugest one that I've probably seen, but it's pretty big. So somewhere write down the 650 calorie, that's what you're you're given and that you're trying to find joules. And then I'm going to go back to the PowerPoint just so you have those conversions. Okay. So 3, 2, 1. All right, I'll switch over. There you go. Okay, so let's take a look at this. So this is a two-step problem. So I'm going to write a flow chart just so you know where my thought processes are. But so I've got the big C calorie. There isn't a relationship for big C calorie to joule directly. I have to go through that little C calorie. And then from little C calorie, there is a relationship to joule. Right? How do these relate? Well, one big C calorie is equal to 1,000 of those little C calories. And then one little C calorie is equivalent to 4.184 joules. So I'm going to first go from my big C calorie into my little C calorie. So if I have 650 big C calories, set this up in dimensional analysis because it's just a conversion factor. The big C calorie goes on the bottom. So one big C calorie is equal to 1,000 little C calories. And then I'm going to just chain them together and go from little C calorie to joules. So for every one little C calorie, I get 4.184 joules. And I didn't flip that up. Yeah. So the big C calorie goes away and the little C calorie goes away. And we're left with just units of joules. And then from there, we just plug it into our calculator, multiply all the things on the top, divide by anything that's on the bottom. For this, it's 650 times 1,000. 650 times 1,000 times 4.184. And we get, erase this sec. This is what my calculator popped out, 2719600 joules. Now I'm going to refine this by rounding to, well, what's 2 sig figs? So 270000 joules. And then I'm actually going to take it a step further. I'm going to put it into scientific notation because this is sort of cumbersome. I wouldn't necessarily go through each of these steps, but I'm doing it so you can see where we end up with that final number. So for scientific notation, we need a number between 1 and 10. So 2.7 times 10 to the however many hops we had to take to get to that. So 1, 2, 3, 4, 5, and 6, 10 to the 6th, and keep your unit of joule. So this would be my final answer. Any questions on that? It's just a conversion factor or a conversion problem using new conversion factors. Okay. So here's another problem. It's talking about a candy bar and it says, I don't know what happened there. A candy bar that's 225 big C calories. How many joules does it contain? Similar problem to what we had, right? So we have the big C calorie, we convert it to the little C calorie, and then we convert it to joules and get our final answer. I think the solution maps, these things do help in the beginning, especially if your critical thinking skills or how do I get from the given to the find aren't maybe as strong as you'd like them to be. Start drawing these things out to give you some help. As you get better at it, it may become a little bit more intuitive for you. So a weight lifted off the ground has a high potential energy and will tend to fall towards the ground to a lower potential energy, right? So mountains tend to weather down to flat environments. They don't weather up unless they're sitting above a big tectonic plate. So this weight up here has relatively little kinetic energy, but it has a lot of potential energy. When the weight falls, that potential energy then changes into kinetic energy. So it's got energy and movement, right? We're transferring it into kinetic energy. When it hits the ground, you may be thinking, well, that energy disappeared. No, the kinetic energy it had didn't disappear. It actually transferred into thermal energy or heat. So the ground will actually get slightly warmer when this weight hits it. Maybe thinking, really, it does that? Well, think if this was much bigger and moving much faster, like let's say a meteorite. If a meteorite hits the surface of the earth, you will definitely see and feel that heat transfer. Okay, this is just a small amount of mass or material, and it's not moving very fast. So the heat will be pretty small, but there is heat produced. So potential energy in unstable materials. So sometimes atoms, molecules will be arranged in such a way that they want to change. They want to break apart or find new partners. TNT has a relatively high potential energy in it because the molecules want to undergo this rapid change to lower their potential energy. When TNT undergoes this change, it releases a lot of heat and energy. So if we're looking at a chemical reaction, we can classify that chemical reaction as being either exothermic or endothermic. And when reading these two diagrams, this is the amount of energy. Here we have reactants, here we have products. So in an exothermic reaction, the reactants, what you're starting with, has a lot of energy. The products have less energy. So the reactants release energy to become the products. If your reactants are releasing energy, they usually release it in heat, the form of heat. So exothermic to exit. In exothermic reactions, the materials will feel warm to the touch. If I have two materials and I pour them together into a beaker and they all of a sudden get really hot, I could classify that as an exothermic reaction. An endothermic reaction is the opposite of that. So in an endothermic reaction, your reactants actually have a lower energy than your products. The reactants steal energy from the surrounding environment to form a higher energy product. In an endothermic reaction, you would have, if I poured two things together, they would get cold or feel cold to the touch, because what the reactants are doing is they're grabbing or stealing thermal energy from your hand, which then feels cold. If you've ever used those ice packs before for an injury where it's like a bag and then it has a secondary bag inside of it and you twist them and break them and then all of a sudden it starts to get cold, that's an example of an endothermic reaction. So when talking about thermal energy is the constant random motion of matter. So when I am measuring thermal energy, I'm measuring its temperature. When I say, oh, this has a temperature of 70 degrees Celsius, I'm actually measuring how much thermal energy or random motion those particles have. So as this thing gets warmer, its thermal energy directly increases and the random motion of the material increases. So the hotter an object is, the greater the random motion of the atoms and molecules that compose it, and hence will have a higher temperature. We don't want to confuse temperature with heat though, okay? So temperature is the measure of the thermal energy of a material. Heat, on the other hand, is the amount of energy that's being transferred from one material to another. So heat is going to have a unit of like joules or calories. Temperature is going to have a unit of degrees Celsius, Kelvin, Fahrenheit. So if I have a cold piece of ice and I drop it into a cup of warm water, that would be an example of thermal energy. The ice is transferring, or rather the water is transferring heat to the ice to warm it up or melt it. We want to make sure we keep those things separate. If you take your hand and you grab a hot pan and you burn your hand, that would be an example of heat or transferring energy. The temperature of the pan would be something that is a property characteristic to the pan itself. Obviously, as the temperature increases, so if that pan is 500 degrees Celsius, it's going to transfer a lot more heat to your hand than if it's 40 degrees Celsius. So these two things are related to each other, but they're not the same thing. As far as how we measure temperature or this random motion, we have the Fahrenheit scale, which we don't use a whole lot, and then we have the Celsius scale and the Kelvin scale. In the Fahrenheit scale, 0 degrees Fahrenheit is the freezing point of a specific concentration of salt solution, which is like, why can't it just be for water? It's not. This is what it is. 96 degrees Fahrenheit is normal body temperature. So, you know, in Fahrenheit, water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. These are very sort of arbitrary random numbers. Celsius is much neater. In Celsius, water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. You want to know those boiling and freezing points. Room temperature for Celsius is roughly 22 degrees Celsius. Now, both Fahrenheit and Celsius can have negative numbers, right? It can be negative 12 degrees Fahrenheit. I don't know if anyone's from up north. I'm from Chicago. So a negative 12 degree Fahrenheit day is pretty normal for January. But those negative numbers that we have in Fahrenheit and Celsius can give us a little bit of trouble when we're running calculations. And if we talk about, you know, what is temperature? Temperature is the measurement of movement of the particles, right? Or the random motion of the particles. So how can you have negative movement? You know, it doesn't really work out. So if we want to avoid negative numbers, we use what's known as the Kelvin scale. So Kelvin, avoid all negative temperatures. The lowest number you can get on the Kelvin scale is 0 degrees Kelvin. This is the coldest temperature possible anywhere in the universe. This is when we, Kelvin, 0 degrees Kelvin is when all particles stop moving. Okay, they don't have any sort of thermal energy. There's no vibration whatsoever. You can't have negative vibrations. So this would be the coldest thing. How do we, sorry, I keep moving. How do we get to a Kelvin? Well, in Kelvin, water freezes at 273, water boils at 373, room temperature is 295. Look at how these numbers are 100 degrees separated from each other. These are also 100 degrees separated from each other. So to get from Celsius to Kelvin, it's really easy. You just add 273. So let's look at some of the calculations. So to go from Kelvin, or rather to go from Celsius to Kelvin, I would take whatever my Celsius is and add 273. This says 273.15. You guys will be fine with just adding 273. Okay, so just know that that's how those relate. Celsius and Fahrenheit, that relationship is a little bit more cumbersome. If I want to get Celsius from a Fahrenheit, I have to subtract 32 and divide it by 1.8. So you do want to be able to convert. So let's do one of these. So given that it's 73 degrees Fahrenheit out, I want you to find both degrees Celsius and Kelvin. So it's 73 Fahrenheit, get me Celsius, and then get me Kelvin. It will be easier for you to go into Celsius first and then convert into Kelvin. I'll give you all 2 minutes for that. Okay, so for Fahrenheit, we've got 73. We want to get Celsius. So we need to take our Fahrenheit, which is 73. We need to subtract 32 from it. And then we need to divide it by what, 1.8. So we end up getting for this 22, and I'm going to give it 1.8, 22.8. Don't stress too much about sig figs with temperature. All right. It can get a little sticky because it's multiplication, division, and addition, subtraction. I'm not going to be really anal about that, so don't worry too much about it. So this is in degrees Celsius. If I want to take that and convert it into Kelvin, that one's pretty easy. We just take whatever our number is to 22.8, and we add 273. Again, so 22.8, we'll add 273. I'm not going to be really strict about the sig fig, so it's 295.8. We can go with 296 Kelvin with that. If you wanted to add the decimal, that's okay as well. So not too bad, right? Just as long as you have the equation, you should be good. Okay, any questions on what we've talked about thus far today? No? Going, gone, okay. So we've got a little bit more on this chapter. The last part does get a little bit mathy, but no worries, nothing more than a 4-variable equation. So we will work on that Wednesday. If you have any individual questions, stay around. If you have any questions about the homework or you're having trouble getting the lab submitted, let me know as well.